Section 2.4 is all about deductive reasoning. We're going to start this section of notes with conditional statements. A conditional statement is one that can be written in an if-then form. We read if P, then Q. Alternatively, you can write P implies Q, is another way of saying the same thing. In symbols, we can say P, and then we've got that double arrow pointing to the right, Q. That in symbols means if P, then Q. An example, if a polygon has 12 sides, then it's called a decagon. That would be a conditional statement. The if part is called the hypothesis, sometimes called the premise or the antecedent. Then it's called a dodecagon. That would be the conclusion or the consequent of the conditional statement. Let me give you a few examples. If you see the statement buy two, get one free, you can rewrite that as a conditional. If you buy two, then you get one for free. Likewise, all squares are quadrilaterals. We can turn that into an if-then. You could say if something is a square, then it is a quadrilateral. I think, therefore I am. You might be familiar with this quotation. It's René Descartes, 1600s. We can rewrite this as an if-then statement. If the hypothesis is true, if I think, then the conclusion must be true. Then I am. So some sentences that are related to conditionals. We have our original, if P, then Q. So for example, all manatees are vegetarians. We can rewrite that as the conditional. If an animal is a manatee, then it is a vegetarian. The converse of a conditional switches around the hypothesis with the conclusion. So instead of P implies Q, it's now Q implies P. We could say if something is a vegetarian, then it is a manatee. Well, and that's ridiculous. There are plenty of vegetarians that are not manatees. So the converse is not always true, given that the conditional is true. Next, the inverse of a statement negates both hypothesis and conclusion. So if P is not true, then Q is not true. For our manatee conditional, we could say if something is not a manatee, then it is not a vegetarian. Well, and that's also ridiculous, because we have plenty of things that aren't manatees that are also not vegetarians. You'll notice the symbols there. We have not P implies not Q. And lastly, the contrapositive switches around the hypothesis with the conclusion and also negates them. So if something is not a manatee, then it is not a vegetarian. So let's talk truth values of conditionals. The conditional and its contrapositive are logically equivalent. In other words, if the conditional is true, the contrapositive is also logically true. Similarly, the converse and the inverse are logically equivalent to each other. And if both the conditional and the converse are true, then we can write a necessary and sufficiency statement, the biconditional. So the biconditional says P implies Q and Q implies P. Take an example, if I'm breathing, then I'm alive. If I'm alive, then I'm breathing. Both of those are true, so the biconditional says I'm breathing if and only if I am alive. That is the biconditional statement. Notice the if and only if in yellow there. It's in between the green hypothesis and the red conclusion. Another way of abbreviating that is with the if with two F's. It's an abbreviation for if and only if. All right, now that we've got some of that vocabulary down, we'll get into deductive reasoning. Inductive reasoning is all about using patterns and examples to make a conjecture. Deductive reasoning uses facts and rules and definitions and theorems to reach logical conclusions. We'll deal with a few laws of logic in our deductive reasoning. The first one is the law of detachment. The law of detachment is also called modus ponens, from the Latin, the way that affirms by affirming, which seems kind of silly, but that's the modus ponens, or the law of detachment. Here's how it works. We assume that the if-then P implies Q is true. P is then asserted to be true for some specific value. We can conclude that Q must also be true. In symbols, we say P implies Q, and then P is true, which therefore implies that Q must be true. Quick example for you. If today is Tuesday, then John will go to work. Let's assume that that is a true conditional statement. We then learn, hey, today is Tuesday. The law of detachment conclusion is, therefore, John will go to work. That is a valid form of modus ponens. Let me give you another example. If a cat purrs, then it's happy. Let's assume that that is a true statement. I don't know if cats actually feel happiness. I guess we're anthropomorphizing, but let's pretend like that is a true if-then statement. We then learn that Fluffy is purring. The conclusion, based on modus ponens, or based on the law of detachment, is that therefore Fluffy is happy. That is a valid argument based on modus ponens. Right? We're concluding that the conclusion is true based on a true hypothesis. Next example. If you give a mouse a cookie, then it will ask for a glass of milk. Let's assume that that if-then is a true conditional. Then we learn the mouse did not ask for a glass of milk. The logical conclusion then is therefore you did not give the mouse a cookie. And that's another true form of the law of detachment. Instead, we're using the contrapositive of the conditional to prove that the statement is indeed true. So this is called modus tollens, or the law of detachment with the contrapositive. Next example, let's go back to cats for a sec. Let's assume if a cat purrs, then it's happy. And Tabby here is happy. What can we conclude? Can we conclude, therefore, Tabby is purring? We can't. So that is not a valid argument. That is the converse error. We assumed that the conclusion was true, therefore the hypothesis must have been the case. And we don't know that that's the case. That is a converse error. One last example along this line. If a cat purrs, then it's happy. Grumpy here is not purring. Can we conclude that Grumpy is not happy? Well, no. We have just shown that the negation of the hypothesis was true. That does not mean that the negation of the conclusion is also the case. One last kind of silly example. Let's say everyone who eats carrots is a quarterback. Now, it's ridiculous, but let's pretend like that if-then is a true statement. If someone eats a carrot, then they're a quarterback. Hey, John over here eats carrots. Therefore, John is a quarterback. That line of reasoning is logically valid. But statement number one makes it kind of questionable. It's logically valid, but I don't know if we say it's a very sound argument. The if-then statement in number one probably isn't there. All right, a few more examples. Let's assume that these if-thens are true. Then we learn Bjorn is a spider. What do we assume? The law of detachment says, therefore, Bjorn has 8 legs. That is a valid argument. Next, let's pretend Sam is a seal. Based on the 3 statements that we have off to the right, there is no valid conclusion that we can make. Next, let's say Pat has 4 legs. You might be tempted to say, therefore, Pat is a dog. The problem with that, though, is you just assumed the consequence, or you assumed the conclusion. You made a converse error. That's not a logical statement. For all we know, Pat is a chair. So that is a not valid line of arguing. Enough with the law of detachment. The next law is called the law of syllogism. The law of syllogism takes two or more conditional statements and forms a string. It forms a chain by combining the hypothesis of one statement with the conclusion of another. So if P implies Q and Q implies R, we can then shorten that to say P implies R. An example, let's say, if Maria is sick, then she will be absent. If she is absent, then she'll miss her classwork. The law of syllogism says we can reduce those two statements into one. If Maria is sick, then she'll miss her classwork. That is valid based on the law of syllogism. Another example here. If it's a sunny day, then I will play outside. If I play outside, then I will lose track of time. If I lose track of time, then I'm going to stay outside too long. Well, if I stay outside too long, then I will get sunburned. If I get sunburned, then I'm going to look goofy in my homecoming pictures. Based on the law of syllogism, we can conclude, if it's a sunny day, then I will look goofy in my homecoming pictures. It's kind of a silly example, and by the way, I did kind of look silly in my homecoming pictures. So there you go. The law of detachment and syllogism.